Hello and welcome to the Sleepy Minds, where we take slow, thoughtful journeys through the wonders of science, one gentle breath at a time. Whether you're resting on the couch, bundled up in bed, or simply looking for a calm companion to wind down your night, I'm so glad you're here. Tonight, we're floating into one of the most quietly astonishing questions in all of science. Does space end? It's a question so simple it sounds like something a child might ask, and yet, the deeper you drift into it, the more it unfurls into a riddle that tugs at the very fabric of what we think we know. What do we mean by end? Anyway, a wall? A border? A curtain we could peek behind if only we had the right telescope? In the next little while, we won't be rushing to find the answers. Instead, we'll float slowly through the layers of this cosmic mystery, like a feather carried by the breeze. We'll pause often, breathe deeply, and allow the edges of the universe to unfold around us. Not as cold facts, but as quiet wonders, too beautiful to rush. And before we gently lift off, I'd love it if you gave this video a like, and maybe even subscribed if you haven't already. It helps the Sleepy Minds reach more curious hearts like yours. I'd also love to know where in the world you're listening from. Are you lying in a warm room somewhere in Cairo as the city quiets down? Or half dozing on a train outside Kyoto with soft rain on the window? Let me know in the comments. I read every one, and it always fills me with joy to see this sleepy little community glow from so many corners of the world. Now, let's begin. You don't need to remember anything. You don't need to focus. Let the words arrive like starlight, soft, quiet, patient. Close your eyes, if that feels right. Take a deep breath, and imagine this. You're standing alone in the middle of a vast desert, under a moonless sky. No cities, no noise, no artificial lights. Just you, and above you, a velvet dome of stars that feels infinite. A river of light swirls overhead, the Milky Way, and as your eyes adjust, the number of stars you see climbs from dozens to hundreds to thousands. You feel small, but not in a scary way. In the comforting, awe-filled way that reminds you, you're part of something big. Really big. And that's where the question lands softly, like a whisper. Does this ever stop? Is there an edge out there, somewhere in that blackness? A place where the universe ends, and beyond it? What? More darkness? A wall? Something else entirely? To even begin unraveling this question, we first have to ask a subtler one. What is space? Really? It's strange to think about. We often picture space as the stage, the backdrop, the empty container in which all things happen. But that view is a bit like thinking silence is just the absence of music. In reality, silence has texture, mood, feeling, and space has structure. For centuries, space was imagined as a simple, unchanging void, a cosmic blank page waiting to be written on by stars and galaxies. Newton, one of the great minds of early science, imagined space as absolute. It was always there, always still, always the same. But then came Einstein. With his wild hair and deeply intuitive grasp of nature, Einstein flipped everything. He proposed that space wasn't a passive arena, it was an active participant. A dynamic, flexible fabric that could bend and stretch in the presence of mass and energy. Space, he said, wasn't separate from time. Together, they formed a unified stage called space-time, and that stage could ripple like the surface of a pond. Imagine laying a thick blanket on the ground. If you place a heavy bowling ball in the middle, the blanket dips. Now roll a marble near the ball. It curves around the dip, caught in the distortion. That's not because the marble is pulled, in the usual sense. It's simply following the warped path of the blanket. That's gravity, in Einstein's world. So, with that in mind, let's return to our original question. Does space end? Already, things are getting more complicated. Because if space can bend and stretch, it means it's not just an emptiness that goes on forever or stops suddenly. It's something, a thing with properties. And like all things, maybe it has a shape. Maybe it loops. Maybe it grows. Or maybe it doesn't end because it's not the kind of thing that can. But let's not leap too far just yet. Instead, let's look at what we can see. When we peer out into the cosmos with our most powerful telescopes, we find ourselves surrounded by a bubble of light. This bubble, roughly 93 billion light-years wide, is what scientists call the observable universe. Now, let's pause here. The word observable is doing a lot of work. It doesn't mean that the universe ends there, like the edge of a map. It simply means this is as far as light has had time to travel to us since the universe began. Light, fast as it is, still takes time to move. And the universe, as best we can tell, is about 13.8 billion years old. But wait, if the universe is 13.8 billion years old, shouldn't we only be able to see 13.8 billion light years in any direction? That would make sense if space were static, but it's not. While light has been journeying toward us, space itself has been stretching under its feet, like a treadmill pulling the destination farther away. Because of this expansion, the farthest light we can see now comes from regions that are much farther than 13.8 billion light years away. The expansion of space has stretched that original distance into something far greater, around 46.5 billion light years in every direction. It's a bit like this. Imagine a firefly sets off across a calm lake to reach your boat. But while it's flying, the lake is growing, the shorelines drifting farther apart. By the time the firefly reaches you, it's traveled much farther than you expected. That's what light has been doing in our ever-expanding universe. So what lies beyond that observable boundary? We don't know. We can't know. Not yet. That region is beyond our cosmic horizon, meaning light from there simply hasn't had enough time to get to us. But, and here's where the beauty begins again. There's no reason to believe the universe just stops there. In fact, every sign we have suggests it keeps going. Possibly forever. Possibly looping back on itself. Possibly branching into realms we can't yet imagine. Still, that bubble of visibility, the observable universe, is all we have. For now. But what a bubble it is. Roughly 2 trillion galaxies, each with millions or even trillions of stars. Countless planets, nebulae, black holes, patterns of light older than Earth itself. And all of it, glimmering faintly within the soft sphere of our view. Now imagine this. You're sitting on a distant galaxy, 10 billion light years from here. From your vantage point, you'd have your own observable bubble, overlapping ours a bit, but stretching into places we could never see from Earth. Which means the observable universe isn't the universe. It's just our slice of it. And maybe that's enough to wonder over for tonight. Before we continue deeper, let's take a pause here. Let your breath settle. Let your thoughts drift. The universe is big. So big, it humbles the mind. But inside that vastness is a kind of peace. A reminder that you don't have to solve every question right now. You just have to be here, for this moment, and let the stars whisper their ancient stories to you.
So, we've established that what we can see, the observable universe, is not necessarily all there is. It's just what light has had time to reach us from. But now, let's let our curiosity float gently into an even bigger question. If space doesn't end at the edge of what we can see, then how far does it go? And what shape does it take? In many ways, this question touches the deepest edges of human thought. Because when we ask, does space end? What we're really asking is, can we ever reach the end of everything? Is there a final destination where the universe runs out or stops being? And just like walking through a forest where the trees never thin out, no matter how far you travel, it can feel both peaceful and unsettling to think, maybe there is no edge. Maybe space simply continues. But is it infinite? That word, infinite, carries a lot of weight. It's not just big. It's bigger than big. It's beyond counting, beyond boundaries, beyond imagining. And that makes it tricky, especially for human brains, which are wired to understand limits. Rooms have walls. Roads have ends. Lives have beginnings and endings. So when we talk about something truly infinite, we're stepping into territory that's hard to even picture. Still, scientists have tried, and their methods aren't guesses. They're built from careful observations, tested theories, and quiet math that whispers what the universe may be hiding. Let's start with something called the curvature of space. You might not think of space as having curvature. It feels flat, right? Straight lines seem straight. Light travels in beams. We don't feel bent or twisted when we look out at the night sky. But space can have curvature, and that curvature tells us a lot about the shape, and potential edge of the universe. There are three main possibilities scientists consider. 1. A flat universe. In this model, the universe stretches out infinitely in all directions. It has no edge, no center, no boundary. It's like an endless sheet of paper, flat and infinite. This doesn't mean the universe is two-dimensional, of course. It simply means that, on large scales, the geometry behaves in a flat, Euclidean way. Parallel lines stay parallel. The angles of a triangle add up to 180 degrees. Light travels in straight paths. And here's the fascinating part. Observations from missions like the Planck spacecraft and WMAP have shown that the universe appears to be very, very flat. At least as far as we can measure, within a margin of error so small it's astonishing. This doesn't prove the universe is infinite, but it strongly suggests that if it does curve, it does so on scales far larger than we can observe. So, a flat universe might go on forever. It may have no edge, no boundary, no stopping point, just an unending, ever-expanding sea of stars, galaxies, and dark mysteries. 2. A closed universe. Now imagine something quite different. A universe that curves back on itself, like the surface of a giant sphere. In this case, space would still have no edge, but it would be finite. If you traveled far enough in one direction, you could, in theory, end up back where you started, like walking in a straight line on Earth and eventually returning to the same point. This kind of universe would be self-contained. You wouldn't fall off it. There would be no wall. But it wouldn't be infinite either. It would be like a cosmic loop. Some versions of this model suggest that the universe might even collapse back on itself one day in a big crunch, the reverse of the Big Bang. But current evidence doesn't seem to support that outcome, at least not with the data we have today. 3. An open universe. Finally, picture a universe shaped like a saddle, curving outward in all directions. This universe also has no edge and no center. It's infinite in extent. But unlike a flat universe, light would behave slightly differently in an open one. Triangles would add up to less than 180 degrees. Parallel lines would diverge. It's a strange, mind-bending shape, difficult to visualize, but mathematically valid. So which model is right? Well, based on our best observations, the flat model currently fits the data best. That means, as far as we can tell, the universe is likely infinite and unbounded. But here's where things get even more quietly astonishing. Even if the universe is infinite, the part we can see is finite. Just our observable bubble. Beyond that, there might be more of the same. More galaxies, more stars, more matter stretching on forever. Or, maybe beyond our bubble, things change. Maybe different laws of physics take over. Maybe the constants we hold sacred, like the speed of light or the strength of gravity, aren't so constant after all. In some versions of the inflationary theory, the early universe expanded in a way that may have created many universes, each with its own set of rules. This idea is called the multiverse, and while it's still very much theoretical, it arises naturally from some of the best supported models we have. So let's pause here. Imagine, you're a drop of dew on a blade of grass. To you, the meadow stretches out in all directions. The horizon is all you can see. But what if there's a forest beyond? A valley? A whole planet you'll never know? That's what the multiverse suggests. That our universe, so vast it humbles every human scale, might be just one tiny bubble in a much larger sea. A bubble with no edge, but not the only one. Still, we have to be careful here. Not all that is imaginable is real. Science walks a delicate path between wonder and evidence. And while the idea of a multiverse is fascinating, we haven't found a way to directly test it yet. So we hold it lightly, like a feather in the breeze. Not discarded, not clutched too tightly, just considered. Now let's return to something a little more grounded. Even if the universe doesn't have an edge in the traditional sense, it does have limits. Not in size, but in what we can reach. Remember, space is expanding. And not just expanding, but accelerating. Thanks to a mysterious force called dark energy, the fabric of space is stretching faster and faster over time. Distant galaxies aren't just moving away from us. They're speeding up. What this means is quietly breathtaking. Someday, Far-off galaxies will move away from us so quickly that their light will never reach us again. They'll fade into darkness, not because they vanished, but because the space between us is stretching too fast for their light to ever bridge the gap. It's like being in a vast ocean where distant ships sail away, not because they've chosen to, but because the water itself is pulling them from view. In the far future, billions of years from now, our night sky may be empty, our cosmic bubble reduced to a lonely island of stars, with the rest of the universe hidden forever behind an unreachable veil. And yet, here we are. Now, in this sliver of cosmic time, we live in a moment of perfect visibility. The universe is old enough that light from the distant past has arrived, but not so old that everything has slipped away. We are poised, right now, in a golden window where we can ask, what's out there? And actually glimpse some of the answers. So, does space end? Not in the way a road ends. Not with a wall. Not with a sudden drop-off. But maybe, just maybe, with a quiet fading. A thinning out. A soft blur at the edges where light grows faint and time stretches long. And even the boldest questions become whispers. Let's rest here, in that thought. Let it settle in your chest. Breathe gently. You're part of a universe that likely has no edge. And yet, your presence here gives it meaning. What a beautiful paradox that is. We've talked about how space may be infinite, about how it has no edges in the way we normally imagine. And yet, the universe is still doing something remarkable. It's expanding. Now that word, expanding, might conjure up images of a balloon being blown up, or an explosion bursting outward into empty space. But that's not quite what's happening. In our universe, space itself is expanding. It's not that galaxies are flying through space away from one another. It's that the space between them is stretching. It's a subtle but powerful difference. To understand this better, let's slow everything down. Imagine a loaf of raisin bread rising in the oven. Each raisin represents a galaxy. As the dough rises, it expands in all directions. The raisins don't move on their own, but the space between them grows. They get farther apart, not because they're traveling, but because the dough itself is swelling. Our universe works in a similar way. Space, the fabric of reality, is stretching. And as it stretches, everything in it drifts apart. This expansion was first noticed by Edwin Hubble, who observed that the light from distant galaxies is redshifted, stretched toward the red end of the spectrum. The farther away a galaxy is, the more its light is stretched. That means it's moving away from us faster. Not because we're special, but because that's what space does. It grows. But here's the truly astonishing part. The universe doesn't expand into anything. There is no outside that space is pushing into. There is only space expanding. This is one of those ideas that's hard to wrap your head around. We're so used to things expanding into something else. A puddle spreading across a floor, a balloon swelling into air, a ripple traveling across a pond. But space doesn't need a container. It doesn't need an outside. In the same way that the surface of the Earth curves in on itself, forming a sphere with no edge, the universe can grow without a boundary. So if it doesn't expand into anything, then what's outside the universe? The short answer is, maybe nothing. Not nothing as an empty space, but nothing as in no space, no time, no physics, not even emptiness, just the absence of everything. But that concept, true nothingness, is extremely hard to define. Every time we imagine nothing, we usually picture something. A dark void, a blank field, a black space with no stars. But even that has shape, direction, depth. True nothingness might not even have those. It may be a state that can't be imagined, because to imagine it is to give it properties, and that, by definition, is something. So maybe the universe has no outside because outside is a meaningless idea in this context. Space doesn't end. It just is, and it changes. Now let's take this a step further. We know space is expanding, but that expansion is accelerating. The farther something is from us, the faster it recedes. And this isn't just motion, it's the stretching of reality itself. A quiet but relentless expansion. What's driving this? That brings us to a concept that has puzzled physicists for decades. Dark energy. Dark energy is invisible. We can't touch it. We don't know what it's made of. but we believe it makes up nearly 70% of the entire universe. And it's the force pushing everything apart faster and faster. Imagine you're floating on a raft in a silent sea, and the water begins to stretch. Not the current, not the wind, but the water itself. Slowly, steadily, endlessly. That's what dark energy is doing to the universe. And it's happening everywhere. Not just at the edges. Not just between galaxies. Even here, in the space between atoms. But at small scales, gravity holds things together. Your body, the Earth, our solar system. Only on cosmic scales does expansion win out. So what happens if this expansion continues? There are a few possibilities, and each one paints a different ending to the story of the universe. 1. The Big Freeze. In this scenario, dark energy continues to accelerate the expansion of the universe. Galaxies drift so far apart that their light never reaches each other. Stars burn out. Matter grows cold and isolated. Eventually, everything fades into darkness. A cold, quiet universe, filled with nothing but drifting particles and dead remnants of stars. It's a slow death, a quiet dissolving, a long, lonely sleep. 2. The Big Rip. If dark energy grows stronger over time, something we don't yet know, it could eventually overcome even the forces that hold galaxies, stars, and atoms together. Space would stretch faster and faster, tearing apart everything, even down to the subatomic level. In this case, there wouldn't just be no edge. There would be no structure. Space itself would rip into pieces. 3. A cosmic rebound. Some theories suggest that expansion might eventually slow down and reverse, leading to a collapse. The universe would contract, galaxies would draw closer, temperatures would rise, and everything might collapse into a new Big Bang. This is the idea of a cyclic universe, expanding and contracting forever, like the breathing of a cosmic lung. But again, current data suggests we're heading more toward a big freeze, not a rebound. The universe is likely to keep expanding endlessly. And so we return to our question. Does space end? In a way, space is like a story with no final page. Not because it goes on forever in a straight line, but because it bends, shifts, and stretches in ways that defy ordinary imagination. It has no wall, no sign that says, "You've reached the end." Instead, the farther you look, the more there is. And the more you understand, the more questions bloom. But here's a thought to rest on. Even if the universe is infinite, you are not lost in it. Your body is made of atoms forged in ancient stars. Your thoughts, these very ones, are patterns carved into space and time by electrical sparks, shaped by a brain that evolved to wonder, to ask, to feel. And that means something profound. You, a finite creature in an infinite universe, are capable of contemplating infinity. And that might be one of the universe's greatest tricks, hiding something boundless within something small. A mind, a spark, a single lifetime, asking, does space end? Let's lie back together for a moment. Close your eyes, if you haven't already, and imagine you're drifting in space. No spaceship, no suit, just you, weightless, silent, suspended in the endless dark, with stars scattered all around like silver dust. There's no wind, no ground, no up or down, just stillness, stretching in every direction. And somewhere out there, maybe billions of light years away, someone else might be asking the same question you are. Where does all of this go? Tonight, we follow that curiosity a little deeper. We've talked about expansion, about the universe stretching without needing an outside. But what if we look closer? Not out into deep space, but into the very fabric of space itself.
Because space, it turns out, isn't empty. Not really. Even in the darkest corners of the cosmos, between galaxies, between stars, between atoms, space buzzes. It hums with a quiet energy, invisible but real. Physicists call this the quantum vacuum. Now, the word vacuum might sound like emptiness, but quantum mechanics tells a different story. At the tiniest scales, far smaller than atoms, space is a storm, a flickering foam of particles popping in and out of existence. Energy surges, vanishes, appears again, Virtual particles dance for the briefest of instants before dissolving back into the void. This isn't science fiction. It's measurable. It's real. It's even responsible for something called the Casimir effect, where two metal plates placed very close together will actually be pushed toward each other. Not by any physical force, but by the pressure of these quantum fluctuations. So even in the emptiest part of the universe, there's still something there. It's as if space has a texture, a restlessness, a memory. And some theories suggest that this quantum foam may be the foundation of everything else. That space, and maybe even time, are not continuous, smooth things, but are made of discrete, flickering bits, like pixels on a screen. If that's true, then maybe space does have a kind of boundary. Not an edge you can bump into, but a limit to its granularity. A fundamental resolution beyond which nothing smaller can exist. Imagine watching a film on an old projector. From a distance, it looks smooth, but zoom in far enough, and you'll start to see the flickering frames, the grain of the film, the space between moments. That could be our universe, a cosmic film reel, playing at the quantum level. And if space is made of something, if it's not just a stage but a substance, then maybe it can change. Maybe it was born. That brings us to one of the deepest mysteries in physics, the origin of space itself. We often think of the Big Bang as an explosion in space. But that's not quite right. The Big Bang didn't happen in space. It created space. Time, too. Before the Big Bang, there was no before. No where. Because space and time didn't exist yet. Try to imagine that. No up, no down, no distance, no time ticking forward. Just non-existence. And then, suddenly, everything. Space bloomed into being. And with it, the rules of physics, the fabric of reality, the gentle unfolding of stars, galaxies, and us. But how can something come from nothing? That question might keep you up at night, or lull you into a kind of dreamy awe. Either way, science is trying to answer it. Some physicists think the universe may have emerged from a quantum fluctuation, a tiny blip in a timeless void, magnified by inflation into the cosmos we see today. Others propose that our universe is part of a larger multiverse, a vast ocean of bubbling cosmic foam, where each bubble is its own universe, with its own laws of physics. In that case, what we call space might just be a pocket, a ripple, one note in an infinite cosmic song. And maybe, just maybe, these other universes brush against ours. Maybe they leave fingerprints. Some scientists even search for signs of cosmic bruising, anomalies in the cosmic microwave background that could hint at collisions between universes. It's speculative. It's dizzying. But it's also beautiful, because it means that space, as vast as it seems, may not be all there is. Let that thought float with you for a while. You, lying here, are part of a universe that may have cousins. Shadows, reflections, worlds governed by different physics, born from different sparks. And yet, here you are, tucked into this particular universe, on a small blue world, listening to the soft hum of science and wonder. Let's return to that floating stillness for a moment. You're out there again, drifting in the quiet. But this time, let's imagine something changes. Something strange. Ahead of you, space seems to fold, bend, ripple like fabric in a breeze. The stars curve around some invisible center, and before you realize it, you're being pulled somewhere. You've just crossed into one of the strangest concepts in all of theoretical physics. The wormhole. Wormholes, sometimes called Einstein-Rosen bridges, are hypothetical tunnels through space-time. You can think of them as shortcuts through the universe, connecting two distant points through a kind of cosmic tunnel. In theory, they're possible. They emerge naturally in the equations of general relativity. And they've long been favorites of science fiction, portals for faster-than-light travel or even time machines. But here's the twist. If wormholes do exist, they would fundamentally reshape how we think about distance. Because if you could travel through a wormhole, space wouldn't be a simple, stretching fabric. It would be foldable, twistable, rewritable. And maybe, just maybe, The end of space is not a wall, but a loop. Imagine this. You travel far enough in one direction, billions of light years, and eventually, you come back to where you started. Not because you turned, but because the universe curves around itself. This is the idea of a closed universe, like the surface of a sphere, but in more than 3 dimensions. You never hit an edge. You never fall off, but you do loop back around. It's a little like those old 1980s video games. Walk off the screen to the left, and you reappear on the right. Space loops. Reality folds. Some cosmological models suggest our universe might be closed like that, finite in volume, but without boundaries, like the surface of the Earth. You can walk forever, but you'll never find an edge. Of course, others suggest the universe is open, infinite, and flat, a cosmos that stretches forever without looping. No curves, just endless forward. So which is it? Right now, the best measurements, using the cosmic microwave background, suggest our universe is very nearly flat, but not exactly. It's like standing on a beach and trying to tell if the Earth is curved. It seems flat, but that might just be because the curve is so huge. And here's the beautiful part. Both possibilities are equally humbling. If space loops, if it's closed, then everything is connected in a grand cosmic knot. If space stretches forever, then it holds an endless sea of galaxies, stars, and possibilities. Either way, we live in something bigger than we can grasp. But maybe there's another question to ask. What lies beyond space? If space expands, what does it expand into? The answer is subtle and strange. It doesn't expand into anything. Instead, more space is created. The distances between galaxies stretch, but there's no external space around our universe. It's like baking a raisin-filled loaf of bread. As the dough rises, the raisins move farther apart. But the loaf isn't expanding into an oven. It's expanding internally. Every part of it grows. So when we ask, what's outside the universe? We might be asking a question that doesn't quite make sense. There is no outside. Space and time are part of the universe, not things it floats inside. Still, the question tugs at us. Could there be something beyond? Some theories say yes.
In string theory and brain cosmology, our universe may be like a membrane, what physicists call a brain, floating in a higher dimensional space. In that view, our 3D universe might just be a slice of a larger, more complex reality with extra dimensions curled up tightly or floating nearby. Imagine a 2-dimensional sheet of paper drifting in a room. The beings living on the sheet might have no idea the room exists. To them, there's only forward, backward, left, and right. No up, no down. But you outside the paper, can see the whole thing. Could that be us? Are we the paper? Are we the fish in the bowl? And if so, can anything pass between the brains? Some physicists have even suggested that dark matter, the mysterious stuff that makes up most of the universe's mass, might be matter from another brain, gravitationally tugging on our own. It's speculative. We don't know, but it opens the door to wonder. Because if our universe is just one brain among many, floating in a higher dimensional sea, then space as we know it may be just the beginning. And does space end? Might really mean, does this brain end? Does our particular slice of reality go on forever? Or does it eventually bump up against something else? Another brain? A wall? A boundary between dimensions? We don't know, but we're listening. We're building detectors, launching telescopes, stretching math to its limits, hoping, always, to catch a whisper from beyond. And as you lie there, tucked under your blanket, drifting somewhere between sleep and stardust, you're part of that great mystery too. You're a thinking piece of the universe, wondering about itself. And that, perhaps, is the most beautiful part of all. Let's follow the pull of gravity, not the gentle kind that keeps your feet on the ground, but the cosmic kind, the kind that warps space so violently it tears holes in reality. Imagine you're drifting through space again, peaceful, weightless, when suddenly, something starts pulling. Slowly at first, but then faster, harder, irresistible. You're falling not down, but in. You've crossed the invisible border of a black hole. This is one of the closest things we know to a true edge of space, a place where our understanding of reality, of physics itself, begins to break down. Black holes aren't really holes at all. They're regions where mass has been compressed into an infinitely dense point, what we call a singularity. Around that point is the event horizon, a boundary you can't escape from once you cross it. Not even light can. To an outside observer, anything falling in seems to freeze at the horizon, never quite vanishing. But for you, the traveler, there's no pause, no signal, just the smooth slide inward, and then silence. What lies inside a black hole? We don't know. Our equations go haywire. Time and space swap roles. Gravity becomes infinite, and the singularity, if it even exists as we imagine, is a point where the very fabric of the universe is crushed out of existence. It might be the ultimate edge, or maybe not. Some scientists now believe black holes might not be endings, but beginnings. Perhaps they're bridges to other universes. Tiny bubbles of space born from the collapse of stars. The idea is called a white hole, a time-reversed black hole, a place where matter comes out instead of going in. Even more radical, what if black holes are gateways? Some versions of string theory and quantum gravity suggest that what happens in a black hole doesn't just disappear. Instead, it's preserved, encoded in the event horizon, and possibly released again, somehow, somewhere. If that's true, then black holes aren't just endpoints. They're transformation points. They might even seed new universes. In that view, the collapse of space here might cause the expansion of space somewhere else. One cosmos ends, another begins, like cosmic recycling. And if universes can bud off from others, then space doesn't end. It evolves. This brings us to one of the most hauntingly beautiful ideas in all of physics, the multiverse. Not just one space, but many. An endless branching tree of realities. Each universe with its own space, its own physics, its own possibilities. Our universe, the one you're breathing in right now, might be just one leaf. Some versions of inflation theory suggest that while our universe inflated rapidly after the Big Bang, other bubbles of space-time may have formed elsewhere. Each expands into its own realm, each invisible to the others. In that model, space doesn't end. It multiplies. And if that's true, then asking, does space end, is like asking, does the ocean end? While looking at a single drop of water. You might be surrounded by vastness and not even know it. Of course, this brings us back to perspective. Let's shrink things down again. Here on Earth, space seems like a void, an emptiness between objects. But it's not truly empty. Even empty space, what we call the vacuum, is buzzing with invisible energy. Virtual particles blink in and out of existence. Quantum fields shimmer beneath the surface. And at the Planck scale, the smallest possible unit of measurement, space might be anything but smooth. It may look more like foam, constantly flickering, constantly shifting. This quantum foam suggests that space itself is not continuous, but granular, like pixels on a screen, too small for us to see. If that's the case, then even nothing has structure, and space itself becomes something you can touch, stretch, and maybe even end. In the sense that, beneath a certain scale, space might stop behaving like the space we know. Now let's zoom out one last time. Beyond the galaxies, beyond the clusters, beyond the cosmic web, at the edge of our view lies something called the cosmic light horizon. This is the farthest distance from which light has had time to reach us since the Big Bang. It's not the edge of the universe, just the edge of what we can see. Roughly 46 billion light-years away in every direction. But here's the strange part. Because the universe is expanding faster than light can travel, some regions are already moving away from us too quickly for their light to ever reach us. They're slipping beyond our view, one galaxy at a time. From our perspective, space is vanishing. Not because it's ending, but because the light from those places can no longer catch up. In time, the universe will darken. The stars will fade. The galaxies will disappear over the horizon. And eventually, we may be left alone in a cold, silent pocket of space, still infinite, but effectively empty. And so, in a poetic sense, maybe that's how space ends. Not with a wall, not with a bang, but with a gentle dimming, a slow farewell, a soft silence. Let's go back in time, not just years, or centuries, or even to the age of the dinosaurs. Let's keep drifting backward, past the formation of the first stars, past the dark ages of the universe, past the moment atoms first came together. Keep going, back through the first seconds, the first microseconds, until we reach a point so dense, so hot, so unfamiliar, that space as we know it hasn't yet unfolded. We've arrived at what scientists call the Big Bang, but the name is misleading. It wasn't a bang, not like an explosion in space. It was more like the sudden expansion of space itself. At the very first moment, time zero, or perhaps something even stranger, our universe burst into being from an unimaginably hot, dense state. Space didn't expand into anything. It was space itself that expanded. There was no outside of it, no pre-existing void.
No canvas onto which the cosmos was painted. Space and time were born together. It's a hard idea to sit with. Our minds crave edges. We want to ask, but what came before? Or, where did the bang happen? But when space and time themselves are part of the event, those questions become slippery. Asking what came before the Big Bang is like asking what's north of the North Pole. The concept loses meaning when you get to the source. Still, we ask anyway, because curiosity doesn't accept easy answers. And the mystery of beginnings is one of the deepest in all of human thought. So what do we actually know? The Big Bang model is supported by powerful evidence. We see the cosmic microwave background, the faint glow of leftover radiation, still echoing across the sky. We observe the redshift of distant galaxies, showing us that space is still expanding, just like the theory predicts. And we can even trace the abundances of light elements like hydrogen and helium back to that primordial fireball. But here's the twist. The Big Bang theory describes the evolution of the universe after that initial moment. It doesn't actually tell us what caused it, or whether it was truly the beginning. In fact, if we rewind the math far enough, we hit a wall, a singularity, a place where our equations break down and stop making sense. It's as if the story ends on a torn page. And maybe that's not the beginning at all. Some physicists now believe the Big Bang wasn't the true origin, but a transition, a moment when something older or deeper transformed into our universe. One idea is called the Big Bounce. In this view, our universe is part of a cosmic cycle, expanding, contracting, and bouncing back again, over and over. Space doesn't begin or end. It breathes. Another possibility comes from quantum cosmology. Perhaps the universe began not as a singularity, but as a quantum fluctuation, a tiny, spontaneous event in a timeless quantum field. In this version, nothingness isn't really nothing. It's unstable, and from that seething vacuum, a tiny bubble of space could have inflated into the universe we now live in. Sound impossible? Well, we've actually seen a form of this before. In particle physics, quantum fluctuations really can create temporary particles out of the vacuum. The idea that something can come from nothing isn't as outrageous as it sounds. Once nothing is redefined, then there's eternal inflation. This model suggests that the early universe expanded at a runaway pace, forming bubble universes like ours all the time. In this cosmic froth, new spaces are constantly being born. If that's true, then our universe isn't the whole story. It's a single region in a vast, inflating multiverse, one bubble among countless others. And if new universes are still budding off even now, then the question, does space end, becomes not just hard to answer. It might be meaningless. There is no singular space. There are many, endless, without beginning or end. But all of this, as fascinating as it is, brings us to a deeper place. A place where science meets philosophy. What does it mean for something to exist? Can space exist without time? Can time exist without change? Is the universe a physical thing, or a mathematical pattern, or a field of consciousness we don't yet understand? These aren't questions with tidy answers, but they remind us that the deeper we look, the more mysterious space becomes. And perhaps that's the point. We often think of space as the backdrop, the empty container in which things happen. But space isn't empty. And it's not just a stage. It's active. It stretches. It bends. It warps under mass. It has energy. It reacts. It even expands. It's more like a living fabric than a passive emptiness. And that fabric, for reasons we still don't fully understand, is growing. Which brings us to a haunting realization. Even though space began, at least our region of it, there may never be an edge. Because the universe is not expanding into anything. It's simply getting bigger. Every point moves away from every other point. The distances stretch like raisins in rising dough. And that rising never ends. It just becomes colder, quieter, and more distant. So maybe space doesn't end in the way we imagine. It ends in intimacy, when we can no longer reach each other. When the galaxies recede. When light can't bridge the gap. When the threads of connection fray into isolation. It ends not with a border, but with separation. When we think of space, we often imagine a kind of emptiness, a blank canvas, a big, black vacuum. But that image is misleading, because the more we've studied the universe, the clearer it becomes. Space is not nothing. It bends. It twists. It can stretch like rubber or ripple like water. In fact, space has structure. It can store energy. It can vibrate. It can even be torn. So, what is it? The key to this question lies not in space alone, but in something deeper. Something that ties space and time together like threads in a single cosmic fabric. Space-time. The term was first introduced in the early 20th century, when a quiet patent clerk named Albert Einstein began thinking differently. He didn't see space as separate from time. He imagined them as part of one unified whole. Before Einstein, we thought of time as a universal metronome, ticking the same for everyone. And space? Just the static, passive stage where things happened. But Einstein shattered that picture. He showed that space and time are relative. They depend on your motion, your gravity, your perspective. In other words, the faster you move, the slower time ticks for you. The stronger the gravity you're in, the slower your clock runs compared to someone floating far from a planet. Time isn't fixed, and neither is distance. This was mind-bending. It meant that reality wasn't the same for everyone. That someone on a spaceship moving near the speed of light would experience time differently from someone standing still on Earth. And it also meant that space itself could curve. Not metaphorically. Literally. Gravity, Einstein proposed, wasn't a force pulling objects together. It was a result of curved spacetime. Mass and energy bend spacetime, and objects follow those curves. Just like a marble rolling around a stretched rubber sheet with a heavy ball in the middle. That's gravity. So now, we're beginning to see that space isn't just the distance between things. It's a living, dynamic entity that responds to mass, to energy, to motion. And it gets stranger, because in Einstein's universe, there's no absolute now. Imagine three people in different places in the cosmos. One standing still, one drifting through space at a steady pace, and one zooming past in a spaceship. To each of them, now, this very moment, could include different sets of events. Something that's happening now for you might be in the past or future for someone else, simply because they're moving differently. It sounds impossible, but it's been confirmed by countless experiments. GPS satellites, for example, have to correct for the fact that time runs differently in orbit than it does on Earth's surface. So if now isn't absolute, and space can bend and ripple, what are we really standing in? It's like the ground beneath our feet is more fluid than solid, more dream than stone. And it gets even deeper when you bring in quantum physics. At the quantum level, the scale of particles and fields, space becomes a jittery, uncertain place. Empty space is filled with activity. Tiny virtual particles blink in and out of existence. Fluctuations ripple through the vacuum. What we once thought of as nothing is now a restless sea. And there's a theory, still being tested, that space itself might emerge from something more fundamental. Not strings, not fields, but information. Some physicists believe that space is not a backdrop, but a result, a consequence of quantum entanglement and relationships between bits of data. In this view, space doesn't exist independently. It's woven from patterns of information. You don't start with space. You start with connections. And from those, the geometry of space emerges. It's a staggering idea, because it means the deepest level of reality may not be physical at all, but mathematical. Or informational. In that case, asking, does space end? Might be like asking, does a dream have a boundary? The dream feels real. It follows rules, but it exists within something else, just like space might. But let's not float too far into the clouds just yet. Back here in our familiar universe, we can still ask, can you reach the edge of space? And the answer depends on the shape of the cosmos. According to general relativity, space can have different geometries. It can be open, like a saddle that goes on forever. It can be flat, like an infinite plane. Or it can be closed, like the surface of a sphere, no edges, but still finite in size. Imagine a two-dimensional creature walking on the surface of a balloon. To that creature, the world appears endless, but it's actually curved back on itself. Now imagine that in 3 dimensions. That's a closed universe. In such a cosmos, you could travel in a straight line forever, and eventually end up where you started, without ever hitting a wall. So again, no edge. Even in a finite universe, there doesn't have to be a boundary. And current observations suggest that space is very nearly flat, maybe even perfectly flat. That leans toward the idea of an infinite universe. But we don't know for sure, because no matter how far we look, we can only see as far as light has had time to travel since the Big Bang. That's called the observable universe. It's a bubble around us, about 93 billion light-years across. Not because the universe is 93 billion years old. It's only about 13.8 billion, but because space has been expanding the entire time. That expansion stretches the light and the distances far beyond what we'd expect. And beyond that bubble, we don't know. There could be more galaxies, more stars, maybe even a mirror image of our own region, playing out alternate cosmic possibilities. Or maybe space eventually curves back, or becomes grainy, or dissolves into something we don't yet have words for. But even though we don't know what's beyond the horizon, we do know this. The fact that we can even ask these questions, that we can stand on a tiny rock orbiting a middling star and wonder about the shape of space and time, that is something extraordinary. We are the universe looking back at itself, measuring, imagining, dreaming. And in a strange way, maybe space doesn't end because we don't stop asking. So far, we've imagined space as a vast, flexible fabric, something that stretches, curves, and evolves. But what happens when that fabric isn't just bent, but torn? Enter the black hole. These are the strangest objects we know. Born from the death of massive stars, black holes represent the deepest wells in space-time. Places where gravity becomes so strong, so overwhelming, that nothing, not even light, can escape. The edge of a black hole is called the event horizon. It's not a wall or a surface. You wouldn't feel anything as you crossed it. But from that moment on, escape becomes impossible. The event horizon is the point of no return, the cosmic one-way door. And inside, things get even more bizarre. According to general relativity, as you fall into a black hole, space and time switch roles. Time becomes a direction you must move forward in, and space collapses inward. At the very center lies the singularity, a point of infinite density and zero volume, where the known laws of physics break down. But is the singularity the end of space? Maybe, or maybe not. Some physicists believe the singularity isn't really a point at all, just a sign that our current theories aren't complete. Quantum physics and general relativity clash at this scale. One treats the universe as a smooth fabric, the other as a jittery, pixelated dance. So to truly understand what's inside a black hole, we need a theory that unites the two, a quantum theory of gravity. Some proposals suggest that black holes might not be endpoints, but gateways. That space, instead of ending, could tunnel through to somewhere else. This is where ideas like wormholes come into play, hypothetical bridges between two distant regions of spacetime. If they exist, and if they're stable, two very big ifs. They could connect one side of the universe to another, or even to a different universe altogether. In that picture, a black hole might not just be a bottomless pit, but a passage. Could you fall into a black hole in our universe and emerge elsewhere? It's an intriguing idea, but there are problems. Even if wormholes exist, most would be too unstable. The moment anything, even a speck of dust, enters one, it collapses. Still, the mathematics allows for it, and the dream persists. And then there's another possibility, that black holes don't destroy information, as we once feared, but encode it on their surface. This is known as the holographic principle, a radical idea suggesting that everything that falls into a black hole gets stored not inside it, but on its outer boundary, like a cosmic memory etched into the event horizon. According to this view, space inside the black hole might not even be real in the way we think. It could be an emergent illusion, just like the idea that space itself might arise from quantum information, which leads to a wild possibility. Maybe space doesn't have an edge because space itself is not fundamental. Maybe it's a projection, a kind of dream spun from deeper relationships. If that's true, then black holes aren't places where space ends. They're places where our understanding ends. They're clues that the true nature of the universe might lie beyond space entirely. But let's return, gently, to something more familiar. Our own place in this cosmic picture. Because while black holes push the boundaries of what we know, they also remind us how much we don't. We can't yet observe the inside of a black hole. We can't see what happens at the singularity. We can't even be sure whether they destroy space, preserve it, or open doors into new realms. And yet, we see their influence. We detect the waves they send out when they collide. We watch stars orbiting invisible giants at the centers of galaxies. We've even photographed the shadow of a black hole, a ring of light bent by gravity around the unknowable dark. The cosmos whispers, and we listen. And what we've heard, so far, is this. Space is not a backdrop. It's a participant. It changes when mass moves. It dances when gravity sinks. It breaks when things go too far.
And in the presence of a black hole, space reaches its most dramatic crescendo, a folding, collapsing, imploding symphony of distortion and depth. Not an ending, perhaps, but a transformation. And maybe that's what the edge of space really is. Not a wall, not a fence, not a dead end in the sky, but a shift. A place where our tools fail, our logic stretches thin, and we are forced to reimagine everything. Because whether it's at the boundary of a black hole, or the farthest reaches of the observable universe, or inside the mind of a dreaming physicist, the edge of space is wherever we are about to discover something new. Let's take a slow breath together. The question of whether space ends isn't just about how far we can travel or how much we can see. It's about how space itself behaves, how it stretches, flows, and maybe even grows. And for that, we need to talk about expansion. It's one of the most surprising discoveries in all of science. In the 1920s, astronomer Edwin Hubble observed that distant galaxies weren't standing still. They were moving away from us. And the farther away a galaxy was, the faster it seemed to be receding. This wasn't because we were at the center of the universe. It was because space itself was expanding. Imagine dots on the surface of a balloon. As the balloon inflates, the dots move away from each other. Not because they're moving on their own, but because the surface itself is stretching. Now imagine that same concept in 3 dimensions. The universe isn't expanding into empty space. There is no outside of the balloon. The surface of the balloon is the space. In our case, space itself is growing, not from a central point, but everywhere, all at once. And that's where things get a little dizzying, because we're not used to thinking of space as something that can grow. We think of it as a container, a stage on which the cosmic play unfolds. But space isn't a container. It's part of the play. When we say the universe is expanding, we don't mean that galaxies are flying away through space like shrapnel from an explosion. We mean that the very fabric of space is stretching, increasing the distance between things, even as they remain still relative to their local surroundings. So, what is space expanding into? Here's the unsettling answer. Nothing. Not empty space. Not darkness. Not void. Just nothing. Because according to general relativity, space isn't embedded in anything. It is all there is. When it expands, it isn't pushing into a background. It's just redefining distance. This is hard to picture. Our brains evolved in forests and caves, not in curved four-dimensional spacetimes. We imagine boundaries, edges, containers. But in cosmology, those rules don't apply. There is no outside of the universe. There is no space beyond space. So if space is expanding and it has no edge, then does it go on forever? Maybe. Some models suggest that space is infinite. No matter where you go, you never run out. Others suggest it's finite but unbounded, like the surface of a sphere. If you kept going in a straight line long enough, you'd eventually end up back where you started. Though in a universe that's always expanding, that's tricky. But this brings us back to something strange. If the universe is finite, it must have a volume, a total amount of space. But if it's expanding, does that mean more space is being created? In a way, yes. Space isn't a thing in the traditional sense. It doesn't need atoms or energy to grow. It's shaped by the matter and energy within it, but it can expand all on its own. This is due to something called the cosmological constant, a kind of pressure built into the fabric of space itself. This pressure acts in all directions, pushing space outward. And the more space there is, the more of this pressure there is, which means more expansion, which means even more space. A feedback loop, a cosmic acceleration. In fact, this is exactly what we observe. Around 1998, scientists discovered that the universe's expansion isn't slowing down. It's speeding up. Distant galaxies are receding faster than ever. And the cause? Something we call dark energy, an invisible, repulsive force that makes up nearly 70% of the entire universe. We don't know what dark energy is, but we know what it does. It drives the expansion of space. So space is not just growing. It's growing faster and faster with time. And this raises a beautiful, haunting question. If space keeps expanding forever, then does everything become isolated? Do galaxies drift so far apart that, someday, we'll no longer see them at all? Will there come a time billions or trillions of years from now, when the sky goes dark, not because stars have died, but because light from distant galaxies can no longer reach us? Yes, in fact, it's already happening. Every second, galaxies pass beyond our cosmic horizon, the farthest distance from which light can ever reach us. Given the age of the universe and the speed of expansion, beyond that horizon, they vanish forever from our view. Not because they're gone, but because the fabric of space is expanding faster than light can travel across it. Think about that. Light, the fastest thing in the universe, can't keep up with the stretching of space. It's like trying to swim upstream in a river that's accelerating faster than you can paddle. No matter how hard you try, the current wins, and the river of space is flowing faster every day. That means the observable universe is shrinking in a very specific way. Not in size, it's still expanding, but in accessibility. Over time, more and more of the cosmos becomes unreachable. It's as if the universe is slowly closing its curtain. Not all at once, but inch by inch, light by light. We are living in the golden age of cosmic observation, a brief window when the universe is still illuminated by the glow of distant galaxies. In the far future, civilizations may look up and see only darkness, unaware that a vast cosmos once shimmered beyond their sky. And yet, even in that growing loneliness, space keeps expanding. No edge, no border, just more distance, more silence, a gentle, endless unfolding. So if the universe is expanding faster and faster, what does that mean for the future? We often imagine the end of the universe as something explosive, a fiery collapse or a final bang. But the more likely scenario is far quieter, slower, colder. It's called the Big Freeze, and it begins not with a bang, but with a drift. As space expands, galaxies move farther apart. The light from those galaxies, the stories of stars and nebulae, of collisions and birth, becomes redder, fainter, and eventually disappears from view entirely. Someday, the only galaxy we'll be able to see will be our own. All the rest will have crossed the cosmic horizon, so distant, so unreachable, that their light can never reach us again. Not in a trillion years, Not ever. And as time goes on, things only grow lonelier. Stars burn out. Planets go dark. Black holes begin to evaporate. A slow whisper of energy known as Hawking radiation. Even the most massive things in the universe, black holes, are not eternal. It might take a googol years, that's a 1 followed by 100 zeros, but eventually, even black holes will vanish. And when they do, there will be nothing left. No stars. No heat. No movement. Just particles drifting in an ocean of nearly perfect stillness. No way to form anything new. No fuel to burn. No clocks to tick. Because without change, there is no time. This is the final silence. But what makes this truly strange is that space will still exist. Time will still exist. The universe will go on expanding, even with nothing inside it. And it will get colder and colder, approaching absolute zero, the coldest temperature possible, where motion itself disappears. This is the big freeze, not a dramatic ending, but a soft fading out. An eternal twilight. And here's where things get even more mysterious. Because as the universe expands and cools, the very structure of space and time may begin to decay. Let me explain. We often think of space as a neutral background, a smooth stage that holds the matter and energy of the cosmos. But what if space itself isn't stable? Some physicists believe our universe might be in a false vacuum, a kind of temporary, delicate balance that could one day collapse. Imagine a ball sitting at the top of a hill. It's balanced for now, but with the slightest push, it could tumble into a valley below. That valley would be a true vacuum, a more stable configuration of space. If such a collapse ever began, in one tiny patch of the universe, it would create a bubble of new reality. Inside that bubble, the laws of physics might be different. Particles might not exist. Atoms might not form. Light might not behave as we know it. And that bubble would spread at the speed of light, destroying everything in its path. We wouldn't see it coming. By the time it reached us, we'd be gone. It sounds terrifying, and it is. But remember, this is just one hypothesis, based on speculative physics and assumptions we don't yet fully understand. And even if it's true, it may not happen for trillions upon trillions of years. Or maybe it already has, and it just hasn't reached us yet. Still, the idea that space itself could change, or end, or transform into something unrecognizable, is enough to give even the calmest minds a little chill. Because we often think of the universe as eternal, but maybe it's not. Maybe space doesn't just go on. Maybe it becomes. Maybe it transforms, evolves, or even dies. But there's another possibility, one that's quieter, stranger, and more mind-bending. Maybe the universe never ends, not in space, not in time, but just becomes unreachable. Already, galaxies are vanishing from our sky. Already, time is slowing in distant places, distorted by expansion. And maybe, someday, even the memory of the universe will fade, not because it was destroyed, but because it slipped beyond the horizon of what any conscious being could ever know. And that brings us back to you, right here, right now. Because in this moment, this one, you are alive in a universe that is still young. You can look up and see stars. You can reach out and feel warmth. You can wonder about galaxies and marvel at light that traveled billions of years to meet your eyes. You are present in the rare window when the cosmos is visible, when the sky is still full of stories. You are here, and that may be the most miraculous part of all, because space may never end. Or it might. But either way, we were here to ask the question, to wonder, to breathe, to dream. Let's pause for a moment. Take a breath. Close your eyes, unless you're drifting off already, and imagine a boundary. Not a physical one, not a wall, but a line in your mind, the place where knowing ends and wonder begins. Because when we ask if space ends, we're not just asking about physics. We're asking about perception. Where does our ability to comprehend stop? What happens when the universe becomes too big, too abstract, too vast for our brains? These soft, wrinkled bundles of neurons, to fully grasp. This is not a failure. It's a frontier. Our minds evolved to throw spears, build fires, raise children, tell stories. Not to intuit the shape of 10-dimensional membranes or quantum foam. But here we are, asking questions that stretch the seams of language. What is nothing? What is everything? Can a boundary exist in a place with no edges? You see, the more we try to define space, the more it slips through our fingers. It's not just the container, it might be the code. Some physicists now believe that space isn't fundamental, that it might be emergent, something that arises out of deeper relationships. Imagine a web, not of silk, but of information. Each thread is a connection, a relationship between particles or fields. The shape of space, its bends, its curves, its distances, might not be absolute. It might simply reflect how things are entangled with each other. In this view, space isn't out there. It's woven from the inside out, a product of connections. That sounds abstract, but think of it this way. If you were in total isolation, no matter, no light, no energy, could you even define up or down? Could you locate yourself without a reference? Space might only emerge when there is something to relate. Some researchers go even further. They suggest we might be living in a kind of hologram, not like a sci-fi illusion, but a universe where the three-dimensional world we experience is projected from two-dimensional data at the boundary of the cosmos. This is the holographic principle, an idea born from black hole physics and quantum theory. And while it sounds fantastical, it has mathematical support. In such a reality, space itself is not what it seems. The volume we live in, the distance we walk, the stars we see, the breaths we take, may be encoded on a distant cosmic shell. Imagine reading a book. The story lives in your mind, in vivid 3D scenes. But the actual information exists in the flat, printed letters. The book doesn't contain a castle, just ink and paper. Yet your mind builds the space. Now imagine that's how the universe works, that you're reading the cosmos, and your mind is the translator. If this is true, then space doesn't end in the way we thought, because it never began, not as a thing, but as a translation, a rendering. This would mean that the boundary of space is not at the edge of the universe, but at the edge of understanding, or even more poetically, at the edge of awareness. Let's slow this down even more. Have you ever dreamed of a place so vivid, so real, that for a moment you forgot it wasn't physical? In that dream, space existed. You walked through it. You reached for objects. You moved through distances. But where was that space? It wasn't out there. It was within you. This raises a radical question. What if physical space, the room you're in, the stars overhead, the blackness of night, is more like a shared dream, a reality rendered not by one mind, but by countless entangled observers, a consensus, a stable hallucination? We don't yet have answers, but quantum mechanics offers clues. In some interpretations, the properties of a particle, its location, its momentum, aren't real until observed. This isn't mystical. It's math. And it suggests that observation plays a role in shaping what we call reality. Could it be that space, this vast, seemingly objective thing, is partly constructed by observation? Could your awareness be the brush that paints the canvas of distance? If so, then the edge of space isn't a physical cliff at the far side of the universe. It's the place where experience fades, where no light reaches, no questions echo back, no awareness remains to measure.
You've F0L'd it before. Looking up at the night sky. That slow, stretching feeling behind your eyes. That sense of looking not just into something, but through it. As if the stars were not just above you, but within you. As if space were a mirror. As if the question, does space end, is the same as asking, do I end? Where do you stop and the universe begin? Your body is made of atoms born in stars. Your breath is filled with particles older than the solar system. Your thoughts are electric whispers riding on the architecture of space-time. So maybe you aren't in space. Maybe space is in you. Maybe every time you close your eyes and imagine the cosmos, you're not traveling outward, you're falling inward. Into the same mystery, the same question. And maybe, just maybe, that's the most beautiful ending of all. Not a wall, not a void, but a return, a reunion with the unknowable. So far, we've gazed into the farthest corners of space and asked, with quiet awe, whether there's an edge, a boundary, a final breath in the expansion of everything. We've looked outward, toward the end of space as a place. We've looked inward, toward space as perception. But now, let's tilt the lens again. What if space doesn't end? Not because it's infinite, but because there are multiple versions of it. Multiple realities. Other universes. A multiverse. Yes, it sounds like something pulled from comic books or science fiction. But the multiverse isn't just a fantasy anymore. It's a serious, if still speculative, idea in modern cosmology. And it arises not from imagination, but from equations. Let's begin gently, with inflation. Not the economic kind, the cosmic kind. Right after the Big Bang, a moment so brief and so bright it escapes normal time, the universe is thought to have undergone a period of inflation, an almost unimaginably fast expansion, stretching the early cosmos like taffy. This inflation smoothed out the universe, ironed out its wrinkles, and set the stage for galaxies, stars, and us. But here's the twist. Many physicists believe that inflation didn't stop everywhere at once. In fact, in most models, inflation keeps happening eternally in some parts of the universe. This leads to a concept called eternal inflation, a bubbling, frothing cosmos where pockets of space stop inflating and become normal universes like ours, while the rest keeps expanding faster than light. Each of these pockets becomes its own universe, with its own physical constants, its own structure, maybe even its own version of physics. We are one bubble in an endless cosmic foam. This kind of multiverse isn't like traveling from one dimension to another. It's more like standing in one room of an impossibly vast mansion, completely unaware of the countless other rooms, each sealed off, each different. And we can't reach them, because the space between us and them is expanding faster than light can travel. In that sense, they are forever beyond our horizon. But they exist. Maybe. Of course, we can't prove it. Not yet. But eternal inflation, ironically, predicts it. And that means the end of our observable universe may not be the end of everything, but just a local lull in an eternal storm of creation. And that leads us to something stranger still. What if there are not only other universes, but other yous? Another version of you watching this video. Another version of you who paused it halfway through. Another version who never found this channel at all. This is the many worlds interpretation of quantum mechanics. You see, in the standard quantum world, particles exist in multiple states at once. A superposition, until they're measured. But what does that really mean? In the many worlds view, all possible outcomes of a quantum event actually occur, but in different branches of reality. When you flip a coin, one universe gets heads, another gets tails. And this doesn't just apply to coins. It applies to every atom, every decision, every heartbeat. You are constantly splitting, not physically, but in terms of possibility. In this view, the universe is not a single story, but an endless branching tree, an infinite forest of realities, overlapping and invisible to each other. If that's true, then what is the shape of space? Is each branch its own universe, its own bubble, its own pocket of space-time? And if so, does space end in one branch but not in another? Maybe in one universe, space is infinite. In another, it curves in on itself like a loop. In another, it has edges we can reach. Which is the real one? Well, maybe they all are. Maybe what we call space is just a stage, a temporary arena where probabilities play out and then diverge. And maybe the edge of space, if there is one, is the moment a possibility becomes real. Not a place, but a choice. It's dizzying, isn't it? You could be lying there in bed, your hand resting on your chest, your mind sinking slowly into sleep, and yet, quantum echoes of you are branching in a trillion directions. One lies still. One rolls over. One begins to dream. Each choice, each moment, a fork. Each fork, a new world. In this view, space doesn't end. It multiplies. Over and over. Forever. And here's where things grow eerily quiet again. What if all of these realities, the bubbles of eternal inflation, the branches of quantum possibility, are not just separate but simulated? What if we're in a simulation? Now, before you roll your eyes or imagine being trapped in a sci-fi video game, let's walk slowly through this idea. It starts with a simple premise. If advanced civilizations ever develop powerful enough computers, they could, in theory, simulate entire universes. And not just visually, but with thinking beings. minds, consciousness. If that's possible, and if even a few such civilizations choose to run these simulations, then the number of simulated minds would vastly outnumber real ones. Statistically, it would be more likely that you are a simulation than the original. That's the simulation hypothesis. And what does this have to do with space ending? Well, if we are in a simulation, then space may only exist where it's rendered. Just like in a video game, the world only loads when you look in that direction. Maybe that's what our cosmic horizon is. Not the edge of reality, but the edge of resolution. A boundary defined not by energy or time, but by processing power. Maybe there's nothing beyond because nothing needs to be beyond, until we try to look. This would mean that space ends when curiosity ends. When no one is watching, the program doesn't bother running. The stars beyond the edge flicker out. The silence returns. And yet, here you are, watching, wondering, which means somewhere out there, real or simulated, space is still being written, still unfolding, still alive with possibility. So, if space does end, or even if it gently fades into something unmeasurable, then the next question we ask almost instinctively is this: what's beyond it? It's a question rooted in how we humans experience the world. A wall implies a room behind it. A curtain begs to be drawn. A road that ends must give way to something. A cliff, a field, a mystery. But what if, for space, beyond doesn't exist? Let's try a simple thought experiment.
Imagine you're standing on the surface of the Earth. It looks flat from where you are, but you know it curves. You could walk in a straight line, forever, and never fall off. Eventually, you'd circle back. There's no edge to the surface of the Earth. Not because the Earth is infinite, but because it loops. Now, imagine space is like that. Not three-dimensional, but four-dimensional. Curved not in ordinary space, but in space-time. In this view, the universe is finite but unbounded, like the surface of a sphere, but in more dimensions than we can perceive. You can travel forever, and you'll never hit a wall. But that doesn't mean the journey never loops back. In such a universe, there is no outside of space, because space itself is all there is. Asking what's beyond space would be like asking what's north of the North Pole. It's not that it's a forbidden place. It's that the concept doesn't apply. Still, our minds resist this. We want there to be something else, something beyond, a realm behind the veil. This desire, this deeply human urge, may be what led ancient philosophers and modern physicists alike to dream of hyperspace, dimensions beyond our own. In string theory, for example, the universe may have more than 3 spatial dimensions, perhaps 10 or 11. Most of these are thought to be compactified, curled up so tightly that we can't see them. But what if they aren't all hidden? What if there are directions we can't move in, not because they're imaginary, but because our very structure is confined to a kind of cosmic membrane, or brain for short? This leads us to brain cosmology. In this theory, our entire universe exists on a 4-dimensional membrane floating in a higher dimensional space, called the bulk. The bulk is not empty space as we know it. It's something more, something richer, deeper, harder to describe. In this view, there might be other brains, other universes, floating in the bulk alongside ours, like sheets of paper in a higher dimensional wind. Maybe those other universes touch ours. Maybe they collide. Maybe they never know we're here. But the key idea is this: our universe could have an edge, a real, physical boundary, beyond which lies a higher dimensional realm. Not space, in the traditional sense, but something beyond it, a backdrop we cannot see or enter, but which may contain the secret to why our universe is the way it is. It's poetic, really, to think that space might end, not in emptiness, not in a cold wall, but in possibility. But it doesn't stop there, because even if the universe has an edge, even if there's a bulk beyond, even if other dimensions cradle us, we are still haunted by another horizon. The cosmological horizon, the limit of what we can observe. We've mentioned it before, but now let's stare directly into it. Light takes time to travel, and the universe is only about 13.8 billion years old. That means there's a limit to how far we can see, because light from farther away hasn't had time to reach us. But here's the twist. The observable universe is not 13.8 billion light-years across, because space has been expanding. Right now, the radius of the observable universe is about 46.5 billion light-years. Beyond that, galaxies exist, or existed, but we will never see them, because the space between us is expanding faster than light can travel. This expansion is not a force. It's not like galaxies moving through space. It's space itself stretching. So we're left with a strange paradox. The universe might be infinite, or it might be finite, but in either case, we can only observe a tiny piece of it. A bubble, a patch of the whole. That means, from our perspective, space ends, not in reality, but in visibility. We can't see past the horizon, not because there's nothing there, but because light itself is caged. And just like a ship at sea sees only the curve of the earth, we see only the curve of time. And beyond that curve, the unknown, the unreachable, the unlit. We don't know if space continues. We don't know what lies past the veil. But we do know this. Every night sky is a kind of horizon. Every telescope is a time machine. And every question we ask about the end leads us deeper into what it means to begin. And this brings us, gently, to the final possibility. What if space ends not in size, or scale, or simulation, but in meaning? What if the question itself has no answer, because it has no clear definition? Think of a rainbow. It looks like it's out there, a real arc hanging in the sky. But try to reach it, walk toward it, chase it. It always stays just as far away, because the rainbow is not a thing in space. It's a relation between your eyes, the light, and the droplets in the air. Without an observer, the rainbow doesn't exist. Maybe space is like that. Maybe it only exists relationally, as the geometry between things, not as a substance of its own. This is the idea behind relational spacetime. In this view, there is no universal grid, no fabric, no container. Space is just a description of how matter and energy relate. Take everything away, all the stars, all the galaxies, all the particles, and space disappears too. There is no empty space, only the absence of relation. So to ask, does space end? Might be like asking, does music end? In a room with no sound. The music ends when the notes stop. The space ends when the relations cease. This is a humbling idea, because it suggests that the boundaries of the universe may not be out there, but in here, in what we can measure, in what we can perceive, in what we can imagine. And that means, you are part of the boundary. Your thoughts, your questions, your wondering, these are not outside space. They are what gives space its shape. You are the music in the silence, the ripple in the void, the question at the end of the answer. So when you ask, does space end? You are really asking, where do I end? And that might be the most beautiful question of all. And so we arrive, slowly and softly, at the edge of everything we know. We've explored the boundaries of the observable universe, wandered through theories of infinite space, curved geometry, multidimensional brains, expanding frontiers, and even questioned whether space is real at all, or just an idea, stitched together by perception. But what does all of this mean for you? For the quiet mind lying awake in the night? For the person staring into the darkness, wondering what lies beyond the stars? There's something deeply moving in this whole search, not just because of the magnitude of the cosmos, but because of how it mirrors something inside us. We ask if space ends, but maybe we're really asking if we end. Are we a fixed thing? A defined edge? A brief flicker in time? Or are we like space itself? Expanding, curving, stretching, rippling with the echo of ancient beginnings. Every time we learn more about the universe, we learn more about ourselves. And what we've learned is this. The cosmos is not static. It's not simple. It's not complete. It's a story, one that's still being written. And we, somehow, impossibly, are part of the pen. The fact that we can even ask whether space ends, that we have the capacity to ponder infinities, to question boundaries, to imagine alternate dimensions, tells us something remarkable. The universe isn't just out there. It's in here, too. In your mind, in your thoughts, in your quiet moments of wonder. And here's something even more beautiful. The universe is under no obligation to make sense. It doesn't owe us answers. Yet, time and again, when we ask deep questions about space, time, gravity, particles, and energy, we get glimpses of structure, hints of elegance, whispers of meaning. Sometimes it's math. Sometimes it's poetry. Sometimes it's just silence. But in every case, it feels like the universe wants to be understood. Or maybe, more truthfully, we want to understand so badly that we shape the cosmos with our questions, molding reality to fit the edges of our awe. That's not a flaw. It's a feature. It's what makes us human. To wonder is to be alive. To not know is to be open. And to ask, does space end? Is not to seek an answer once and for all, but to live within the question. That's the gift of curiosity. It keeps us moving. It keeps us exploring. It keeps us awake, even in the dark. So maybe the end of space is not a line, or a wall, or a void. Maybe it's a mirror, one that reflects back to us the limits of our knowledge and the endlessness of our desire to know more. The edge of the universe is not where the galaxies stop. It's where your understanding stops. And every time you learn something new, every time you stretch your thinking just a little farther, that edge recedes. You make the universe bigger by being part of it. That's not metaphor. That's physics. That's philosophy. That's you. Now, before we close, let's take a moment to return where we began. Imagine, once more, the night sky. Silent, vast, endless. Maybe you're on a rooftop. Maybe you're lying in bed. Maybe you're nowhere at all, just floating in thought. Above you, darkness sprinkled with light. Around you, a cosmos still unfolding. And in this stillness, something strange happens. You stop trying to grasp the universe, and you start to simply feel it. Not as a puzzle to be solved, not as a territory to conquer, but as something sacred, quiet, alive. You begin to sense that asking if space ends is not about finding a final answer. It's about learning to sit with mystery, not as a failure of knowledge, but as a kind of communion. Because in the end, whether the universe is infinite or finite, whether it loops or stretches or bubbles or ripples, whether it ends in silence or begins again somewhere else, what truly matters is that you are here, right now, in it, of it, a momentary arrangement of particles, aware of itself, a tiny island of consciousness in a vast, expanding sea. And somehow, impossibly, you're able to look out and ask questions like this. That is astonishing. You are the observer, the dreamer, the question itself, and the universe. This strange, elegant, maddening universe is the mirror that answers back. So, does space end? Maybe, maybe not. But one thing is certain. The journey to find out never ends. And for as long as there are minds to wonder, eyes to gaze, and hearts to feel small beneath the stars, the universe will continue to expand, not just outward, but inward too. Into imagination, into discovery, into you. So rest now, fellow traveler. Let your thoughts drift like comets. Let your dreams echo across galaxies. And remember, the edge of space is not the end. It's just the beginning of the next question. If your eyes are starting to feel heavy, if your thoughts are still swirling like distant galaxies, that's okay. You don't need to remember any of this. You don't need to hold on to curved space or cosmic inflation or the edge of the observable universe. Just let it all drift, like stars sliding behind clouds, like waves receding on the shore of sleep. Because this journey, this slow, dreamy wander through the question, does space end, wasn't meant to give you answers. It was meant to give you peace. A soft place to rest your thoughts, a quiet rhythm to carry you into stillness. And if you've made it this far, thank you. Truly, you're part of something rare and beautiful, a community of curious minds, asking deep questions under the stars. So if you enjoyed this journey, even if you're only half awake, you might consider gently tapping that like button, or maybe subscribing to the Sleepy Minds, where we explore the strange and wonderful science of everything, slowly. And if your mind is still wandering, you might check out some of our other videos, stories about dreams, about cells, about time itself. But for now, just breathe. You are safe. You are small. And you are part of something unimaginably vast. The stars will wait for you. And the next question will be here when you wake. Good night, fellow explorer. Sleep well, and keep wondering.